Hello everyone, welcome back our class. We continue study chapter 6, thermodynamic relations, section 5, general relations of internal energy. Last section we have learned how to use PV or TP or VP to express the enthalpy ds. This section we use the same way to express du and dH. We know du equals Tds minus Pdv. P and V is easy to measure. T also easy to measure. So we use last section ds, the function, into equation 11. We can obtain, very easy to obtain, the second and third du equation. Just here, du equals Cv dt minus P minus T times partial P partial T, V is constant, dV. So equation 39 is dH equation. The second du equation, the 39 equation is first du equation. The equation 40, du equals Cp minus P partial V partial T, P is constant, times dt minus T partial V partial T, P is constant, plus P times partial V over partial P, T is constant, times dP. This equation is very long. Equation 40, we can call it the second du equation. The third du equation is Cv partial T partial P, V is constant, dP, plus Cp times partial T partial V, P is constant, minus P, together, dV. This equation also is come from the third ds equation. So we can call it the third du equation is equation 41. du. The first du, the second du, the third du equation just come from 11 equation. Equation 11 and the first ds, second ds, the third ds equation. At the same thing, the general relations of enthalpy, dH equals Tds plus Vdp, equation 12. We use the first ds equation, the second ds equation, the third ds equation into this equation. We easily obtained the first dH equation, second dH equation, the third dH equation. 1, 2, 3. Just here, maybe someone is very long, very complex. But for convenience, we can select the simple one. For example, here, maybe the 43, the equation may be more simple. Certainly, we can use this one to calculate the dH by T and P. That's the first, second, and third dH equation. The method is same because ds equation we obtained. Okay, in this page we give an example. In this example, please give the relation of T and V for the van der Waals gas in a Bedical process, assuming Cv is constant. This example is a little simple. It's not so difficult. Solution. For van der Waals gas, we have, because van der Waals equation is easy obtained. From the van der Waals gas equation, we obtained partial P, partial T, V is constant, equals R over V minus B. R is the gas universe, B is constant. Then, from the first ds equation, ds equals Cv over T dt plus partial P, partial T, V is constant. Because partial P over partial T, V is constant, equals R over V minus B. So the ds become R over V minus B dV. This equation, this full differential just come from van der Waals gas. Van der Waals gas. Okay, from the adiabatic process, because the condition tell you the process is adiabatic process. So in this case, ds is 0. ds is 0. So we obtained Cv dt over T plus R dV over V minus B equals 0. Because here R and B is constant. Cv also is constant. Okay, we can do integration. Obtain Cv ln T plus R ln V minus B is constant. Finally, we obtained T times V minus B power R over Cv is constant. Here is the solution. The section 7, we especially discuss some thermal coefficient. From the state equation, f pvt, f is function, equals 0, we can get 3 partial differential. First is partial P, partial T, V is constant. The second is partial V, partial P, T is constant. The third one is partial V, partial T, P is constant. We use these 3 partial differential to define 3 thermal coefficients. The first is coefficient of thermal expansion, alpha P. Definition is alpha P equals 1 over V times partial V, partial T, P is constant. Equation 27. So alpha P has the unit Kelvin power minus 1. Here is the coefficient of thermal expansion, alpha P. From this equation, we can calculate the thermal expansion. Thermal expansion coefficient certainly is a thermal properties of substance. Another thermal coefficient is constant temperature compression coefficient, beta T. Beta T definition is beta T equals 1 minus 1 over V times partial V, partial P, T is constant. It is equation 28. The third coefficient is temperature coefficient of pressure, kappa. Kappa equals 1 over P times partial P, partial T, V is constant. It is equation 29. Alpha, beta, kappa is 3 coefficient of substance. Thermal coefficient of substance is very important. We can use the coefficient to build the state functions. So it is very important. Here we easy to find the unit of kappa is K power minus 1. 1 over K, or to say. From the mathematics, the unit of beta T is 1 over Pascal, or Pascal power minus 1. Power first. So beta and kappa. All of them with the unit. The relationship between thermal coefficient, we have learned several coefficients. So we can build their relation, alpha, beta, kappa. We obtained alpha p over beta t equals partial p partial t, v is constant, also equals p times kappa. It is the equation 30. Adiabatic compression coefficient beta s is defined as beta s equals minus 1 over v times partial v over partial p. S is constant. S is constant means adiabatic compression. Beta s has unit as Pascal, power minus first. So beta s is always positive. Adiabatic throttling coefficient mu j equals partial t partial p, h is constant. We can very easy from the adiabatic throttling coefficient, throttling process, we easily obtain this coefficient. Also, this coefficient is very important. Another two coefficient is very familiar. They are CV and CP. CV, the definition is partial U partial T, V is constant. CP equals partial H partial T, P is constant. So the equation 30, equation 31, equation 33, 34, 35 consist several very important coefficients of substance. Okay, thank you.